Swayam Prabha. Digital India. Educated India.
In the previous lecture, we studied a rigid rotor which was mounted at ends by springs, and the spring property in two orthogonal directions were different. Such model is valid for bearings in which rolling elements bearings are there, and generally it imparts the stiffness. Damping is relatively low, and the stiffness property in two directions may be different. Now, if we are considering the hydrodynamic bearing, then these property not only changes the stiffness in two directions, in vertical and horizontal direction, but also it imparts damping in the two orthogonal direction. Apart from this, there is a cross coupled stiffness and damping in the such kind of bearing. So, what are these? We will see in the present lecture how these stiffness and damping can be derived either by a theoretical model or through experiment. That basic outline we will study, and then we will study when a particular rigid rotor is mounted on such complex bearings, how its behavior take place. This is the overview of the lecture. This is rigid rotor mounted on an anisotropic spring and damper as bearings. Then even will study the force transmitted through the bearing from the rotor, and in this we will be having the following concept to be covered in this particular lecture. There is a bearing 8 linearized parameter model, cross coupling, stiffness and damping, and orbit of the shaft. So, let us take a hydrodynamic bearing, and in this particular bearing, this is the bearing center. When the journal which is inside, this is the bearing. When it is not rotating, then we expect it will be resting at the bottom of the this bearing, where omega is 0 for this particular case. But when this particular speed increases, you can able to see whatever the fluid which is here, which is in the clearance, it will try to go into this particular wedge, and because of this the pressure will be generated at the wedge, and this particular journal will lift on inside the bearing. So, I am drawing a particular configuration in which the journal is rotating at particular speed, and it has taken some equilibrium position inside the bearing. So, now you can able to see that because of the rotation of the journal, the fluids are getting pumped in this wedge part, and because of that the pressure is generated in this region, and the weight of the journal is supported by the pressure generated at the fluid film. In this particular case, let us say this is the bearing center and this is the journal center. This journal center and bearing center are offset by some amount. Let us say Bj is the radial eccentricity, and if we draw a vertical from the bearing center, this particular angle is called latitude angle, which defines the position of the journal. So, if we want to plot the journal motion, how it changes its location with respect to speed, because for a particular speed it occupies certain position inside the bearing, and so you can able to see that at rest it is here. This is the journal center, this is the bearing center. Now, as speed increases, it changes its position, and theoretically when speed is at infinity, it reaches to the B. That means both the rotor and journal center, journal and the bearing center will be at the same place. So, we can able to say when speed is increasing, the shaft center takes this particular path, and for one particular speed it will occupy this particular position, and this is the radial eccentricity which we have drawn here, the Bj. This is the journal position. Let us say at equilibrium for a particular speed, its position is given by u naught and v naught. This is the altitude angle. So, E, R and phi define the position of the journal, or even we can able to define with respect to v naught and u naught. Now, now you can able to see that when we are changing the speed, this particular journal changes its position, and if we talk about how the fluid film is imparting the stiffness and damping to the rotor. So, obviously, we expect that when we are changing the speed, when the journal position is changing, we expect it will be having different stiffness and different damping property. So, now let us analyze those here. The fluid film which is giving a reaction force onto the journal is Ru in the direction of horizontal direction, and this reaction force is function of the position of the journal and the instantaneous velocity also. The fluid force in the vertical direction also is function of this quantity. So, these are the reaction forces which is coming from the fluid film onto the journal. Now, this is at equilibrium position, let us say. That means it is at, let us say, u naught and v naught. If we are giving some kind of perturbation or disturbance from its equilibrium, then let us say we are giving perturbation to each of this by du, dv and its velocity components to each of these variables. So, the fluid film force now will be written as, so this fluid film force we expect that it will be changing because of this disturbance. Like this. Similarly, now this particular is in u direction, similar variation will be there in the v direction also. This particular function we can able to expand using Taylor series expansion. So, let us say the reaction force in u direction due to the at equilibrium position plus the variations components. So, this is the variation in the du, then variation in the dv and the velocity components. These are the velocity components. A similar variation we can able to express in v direction. So, this will be v plus dv. I am again repeating this. So, similar variation will be there in the v direction force velocity components. So, this will be equal to the force in vertical direction at equilibrium and variations. This we are doing with the help of Taylor series expansion. These are the velocity components. Change in the force due to the velocity components in horizontal and vertical direction. Now, you can able to see that this particular force is the force due to the initial equilibrium position and the disturbance. Now, the change in the force in the u direction and v direction we can able to get by writing this particular u, which is function of all those functions, minus at equilibrium. So, this can be written as this particular expression that I am writing as, let us say, k u into du. Then this expression I am writing as a coefficient k u v dv. The first subscript I am representing to the numerator and the second subscript to the denominator. So, numerator is having force and denominator is having displacement. So, this is representing the force direction and this is representing the displacement direction. Similarly, these are corresponding to the velocity. So, I am writing this as c u as a subscript du plus c u v and dv dot. So, here also the first subscript is in the force direction u direction and second is in the displacement direction, that is the velocity direction. So, the change in the fluid forces I am writing like this. Similarly, we can able to write in the other direction, that is in the v direction. So, the change in the force in v direction will be k v du plus k, sorry, this will be u v and du, and then it will be v dv plus c v u du dot plus c v dv dot. So, you can able to see that this k and c which we are represented, this is representing the change in the force for a small perturbation in the displacement, and this is representing the change in the force due to the change in the velocity. So, actually this is nothing but the stiffness, which is stiffness is defined as change in the force with respect to the displacement, and this is the damping coefficient, which is defined as change in the force due to the velocity. So, these are stiffness coefficients and damping coefficients. So, if we take one particular coefficient, let us say u v. So, this is representing change in force, fluid film force in u direction divided by change in displacement in the same direction, that is in the v direction, because I have taken the different subscript v direction. So, this particular stiffness. So, this particular stiffness K U V I have defined, in which we are taking the force direction u, the change in the force in u, and the displacement in the v direction. So, this is a cross coupled term. So, in this particular case, if we are considering a rotor which is supported on such bearing, hydrodynamic bearing, if you are giving a force in u direction, that is horizontal direction, there will be displacement in the horizontal vertical direction also. So, that means if you are giving force in horizontal direction, displacement will take place in that direction as well as in the vertical direction, and when it is taking, the displacement is taking in the other orthogonal direction, then those terms are called as cross coupled terms, and those terms which are giving the displacement in the same plane, they are called direct terms. So, in this particular case, we can able to write these coefficients like this, because we have defined four stiffness terms and 4 damping terms. So, in this you can able to see this u, k u u, k u v, and this is k v u, and this is k v v. So, these four stiffness term, and similarly we have 4 damping term u v and v u and v v. So, in this this and this, they are called direct stiffness term, direct stiffness coefficients, and these two are called cross coupled stiffness coefficients. Similarly, here these two are direct damping term, and these are cross coupled damping terms. So, in this particular case, if we want to define the CUV, so this is the change in the force in v direction due to change in the velocity in the v direction. So, change in the force in u direction due to change in the force in the v direction. Generally, these stiffness and damping coefficients which I defined for fluid film bearing, we have seen that they are 8 in number, 4 are for stiffness term and 4 are for damping term. They can be calculated by either calculating the change in the fluid film force for a given displacement in particular direction. This change in the fluid film force, either we can able to calculate using the lubrication theory, using the Reynolds equation, and or sometimes people perform the experiments and they give this particular displacements or velocity, and they measure the fluid film force, how much they are changing, and with the help of these ratio we can able to get this stiffness and damping coefficients. Now, once we have the idea of this particular model, we will analyze a rigid rotor which is mounted on these kind of bearings having 8 linearized stiffness coefficients. In this particular case, you have seen that when we expanded using the Taylor series, these expressions, we retain only the first derivatives, higher derivatives we neglected. So, basically we have linearized the fluid film forces, which is actually nonlinear in nature, so that we can able to do some kind of analysis by which we can able to understand either the critical speed calculation of the rotor, or even we can able to do the instability analysis in subsequent lectures. Now, we will analyze a rigid rotor which is mounted on this kind of fluid film bearing having damping and stiffness terms, not only in one direction, but in the orthogonal direction also. And apart from these, we have cross coupled stiffness and damping terms. So, let me write this as C y y, this is K y y, this is C x x, and this is K x x. This is cross coupled term. Let us say this is C x y and this is K x y. Similarly, we will be having another cross coupled term. So, these are K y x and C x y. So, and this is one end of the bearing. Similarly, other end of the bearing will be having these terms. So, this particular rotor is mounted on two identical bearing, let us say, for this particular analysis, and is having both direct as well as cross coupled terms. So, you can able to see there are springs and dust spots which are 8 in number at each end of the bearing of the shaft. So, basically in this particular case I am representing, because now I am using x, y, z coordinate system. So, I am this z axis direction and we have y and x in this direction. So, these stiffness and damping, they are giving the forces, fluid film forces in the x and y direction. That is why I have changed the subscript of the coefficients to x and y. So, basically we can able to see that now these this particular rotor which is mounted on to the two bearings is identical to the previous analysis. Only thing is now we are having so many spring and damper coefficients attached with this. So, if when we draw the free body diagram of this particular rotor on the similar lines as the previous lecture. So, let us say I am drawing the free body diagram in the YZ plane, and in this particular case also we are assuming that we do not have any coupling of the translatory motion and the rotary motion, they are uncoupled. That means, if you are giving a shaft a vertical motion or a vertical force, there will not be any tilting. There can be displacement in other direction or velocity in other direction, that will be translatory in nature, but translatory and rotary motions are not coupled. And if on the same line we can, if we are giving a tilting motion to the rotor, it will give tilting in two planes, but it will not give any linear displacement or translatory displacement. So, with that assumption we are analyzing this, and so I am giving a pure translatory motion. So, I am giving a displacement in the y direction. So, this is the displacement in y direction, and we expect because of this there will be displacement in x direction also in other orthogonal plane. And earlier we had both the radial and axial eccentricity of the rotor. So, this is the axial eccentricity in the z direction, and because is rotating, we have this centrifugal force which is offset from the center of the shaft. Now at ends bearings are there, they will give forces. This time the forces will be not only from the spring, this was the term which we used in the previous analysis, but now because of the cross coupled term we will be having some more terms, like due to the displacement in x direction, because cross coupling is there now between two linear displacement direction. Apart from that, we have damping term also, and we have the cross coupled due to the damping. So these are the forces which are acting at the left hand. Same force, because I am considering in this particular analysis same bearing, so the same force will act in the other end also. Due to the damping and stiffness. So this is the free body diagram of the shaft. This dotted line represents the shaft center line and is acted upon by centrifugal force here, and bearing reaction forces because of displacement in the x and y direction, because now this x and y displacement we cannot able to separate it out. So both the forces will be coming in this particular model. So now we can able to write the equation of motion by putting the equilibrium equation. So we can able to write the equation of motion like this. So because centrifugal force is acting in positive direction, so that will be positive quantity. Then these bearing reactions there, we can able to add them because two bearing forces are there. And from damping, and that should be equal to mass into acceleration in the y direction. So this is one of the equation of motion. Now we can able to write similar equation of motion if we give a motion in the x direction or the equilibrium in the zx plane. So that will be the centrifugal force will be me omega square cos omega t minus the subscripts would change here, and here it will be 2xy, and for damping we will be having cxx x dot because of velocity and cxy due to velocity in y direction. This should be equal to mass into acceleration in x direction. So this is the second equation of motion. These two equations you can able to see that we have in both equation x and y terms, but the tilt motion is not there because we are not considering in this particular model the coupling between the translatory and the linear or the angular motion. Now on the same line we can able to go for the tilting of this particular rotor. So I am drawing the free body diagram in y and z direction, in y and z plane. So the positive tilting direction is from y to z, and this is the tilting angle phi x, because that tilting is about x axis. Now because of this tilt we have this much deformation of the shaft. So that is phi x if length of the shaft total is L. So this will be L by 2, and this side also. So you can able to see that here the spring is getting compressed, so force will be upward. Here it is getting extended, so this will be downward, and the values of these the forces will be the displacement this we wrote in the previous analysis, in the previous lecture. Now, apart from this force, there will be forces due to the cross coupled stiffness. This is due to the cross coupled stiffness. Sorry, this is x, this is x, and this is y, because this particular force will come due to the displacement and tilt in the about the y axis. Similarly, we will be having damping terms. So, in this particular case, we will be having, instead of displacement, derivative of this, and additionally due to coupling we will be having another force term, that will be due to velocity in the about the y axis, this one. The similar force will be there at this end also, because we have considered this particular bearing same as other end. Apart from that, we will be having this centrifugal force, which is E z. So, now we can able to see, we can able to write the moment equation. This particular force is acting this side also, and the moment due to this centrifugal force we can able to balance to the rotary inertia. So, we can able to write let us say a moment m e omega square sin omega t into E z is the moment. This is giving moment in the counterclockwise direction, that is opposite to the angular displacement. So, it will be negative, and this force and this force will give a moment again opposite to the displacement, angular displacement direction. So, they will also be negative. So, this will give us 0.5 kyy. L is the moment arm. So, we will be having L square. So, these are the moments now. They are negative because they are acting opposite to the angular displacements. So, here we are getting 4 terms from the fluid film forces. Earlier it was only single term. This should be equal to the diametral mass moment of inertia of the rotor into acceleration, angular acceleration in the y direction, that is in the this particular plane the tilting is about x axis. So, this is another equation of motion. On the same line we can able to write another equation of motion in other plane, that is in x z plane. Here cos omega t will come, and here subscript would change, angle subscript will also be changing. X y L square phi y 0.5 C x x. This will be x x L square phi dot y and minus 0.5 C x y L phi y dot should be equal to I d. This will be in the about the y axis. So, this is the fourth equation of motion. Now, we have seen that we could able to get the equation of motion in 4 direction, that is in the x, y, phi x and phi y direction, and these form of the equations are similar to the previous one. Now we can put these equations in a matrix form, and we can able to analyze for the unbalanced response. So, these equations we can able to put in a matrix form like this: mass matrix, stiffness matrix, or damping matrix, and then stiffness matrix is equal to the external force, which is due to the unbalanced force. And the form of the mass matrix for this case will be like this. It depends upon how we have stacked the displacement vector. So, in this particular case, the displacement vector x, we have stacked like x, y, phi y and phi x. The ordering of this stacking we can able to change without any problem, but only thing is these coefficients will change its position if we are changing the ordering of this. Similarly, the damping stiffness, damping coefficients will be now because of the cross coupled terms. Now we are getting 4 terms. Earlier only single, only this direct damping terms were there. Earlier damping term was not there totally, but now we are having this all 4 components, and also due to the last 2 are corresponding to the moment balance. So, we have 0.5 L square C x x, 0.5 L square C x y, and that is C y x, and this is C y y. Now, the stiffness matrix will be having similar form. I will give you that in the next slide. Earlier this stiffness matrix had only diagonal terms. Now, because of cross coupled terms, we have off diagonal terms also. And these terms are corresponding to the moment balance. This cross coupled terms were not there earlier, only direct stiffness terms were there. So, in the previous analysis, previous lecture, we had these diagonal terms. Now, these off diagonal terms are coming into the picture. Basically, if you see these off diagonal terms, because they are getting multiplied by the linear displacements or translatory displacement. So, they are coupling the motion in 2 directions, and these are coupling the motion, tilting motion in 2 directions, but these terms are 0, that represent that there is no coupling between the linear motion and the angular motion. So, here you can able to see these are 0. So, the linear motion and the angular motions are not coupled for this particular analysis. So, once we have defined all the matrices, only the force is left out. The force we can able to write here. The force will take the shape of, because we have, I am taking something common here, m e omega square, that is common. So, apart from that, we have sin omega t, cos omega t in the, that is, sorry, this should be cos omega t and sin omega t in x and y direction. These are forces, and then moment will contain E z also apart from cos omega t and sin omega t. So, this is the force, external force vector. Now, this can be solved using the procedure described earlier. We can able to assume the solution of the response as complex amplitude and j omega t. So, this will give us x dot as j omega capital X e j omega t, and acceleration double dot of this will give minus omega square x e j omega t. This can be substituted, this solution can be substituted in the equation of motion these, and we can able to get minus m minus omega square m, x I will be taking common, then j omega c plus k I am taking x common, e j omega t. The force vector we can able to write this particular force vector, which for unbalance was there, we can able to write amplitude and this time dependent term, which we earlier defined how this cos omega t and sin omega t can be written in this form. So, this will give us j omega t. So, this will get cancelled. So, we have if we define this particular matrix as A, so the unbalance we can able to get as inverse of A into force. So, this is the solution for unbalance. We can able to solve this unbalanced response x, which is having 4 components in linear displacement and angular displacement in 2 directions. So, you can able to see here omega spin speed of the shaft is variable. We can able to solve this particular response for various spin speed, and we can able to plot how these are varying with speed. So, wherever we will coincide the natural frequency with this speed, the resonance will take place. Those are the critical speeds. Now, this particular problem of rotor supported on anisotropic bearing will see through one numerical example how this unbalanced response can be obtained for various speeds. For this, I have taken one problem in which we are obviously interested in the transverse critical speed for rotor bearing system, which is there is a rigid shaft which is supported on 2 anisotropic bearing. The shaft is symmetric. So, and the length of the shaft is 1 meter, the diameter of the shaft is 0.05 meter, the mass density is given, the shaft is supported by flexible bearings, and we are considering motion both in the vertical and horizontal plane, because we are considering the bearing property with 8 coefficients, that is 4 for damping and 4 for stiffness. So, these are the stiffness property kxx, kyy, these are direct stiffness, these are cross coupled stiffness. They are generally relatively smaller in magnitude as compared to direct stiffness. And similarly, the direct damping terms and cross coupled damping terms are there, and in this particular case not only we are considering the bearings which are there at the left hand and right hand, we are considering the different bearings, so that we can able to generalize this particular method. So, this is the other hand bearing, the right hand side bearing. So, is having another 4 coefficients of damping and stiffness. So, this is the shaft, rigid shaft supported on 2 different bearings, and some more data are there. We need to get the unbalanced response. So, what we are doing, we are obtaining the natural frequency of the system, this system, and also through unbalance we are obtaining the critical speed, and we are cross verifying whether we are getting the same values through free vibration and forced vibration. So, in this particular unbalanced response, we will be having this particular eccentricity of the unbalance. So, we already defined earlier the mass matrix. So, we can able to calculate the, because we have all the geometry and material property of the shaft, we can able to get the mass, diametral mass moment of inertia of a cylinder, which is a rotor, is given by this, where r is the radius, l is the length of the rotor. So, and m is the mass of the rotor, which we can able to get from here. Rho is the density of the material, L is the length of the shaft. So, from this we can able to form the mass matrix. The stiffness coefficients which we have which is given can be, this is the stiffness matrix. So, you can able to see these two stiffnesses two different bearings are getting added up here. So, there is small change in the stiffness matrix which we obtained earlier. It was symmetric. So, we had 2 kxx, now they are different. So, we are adding them separately. Similarly, this. So, if we substitute those given value of the stiffness and the length, we can able to get the stiffness coefficient like this, stiffness coefficient matrix like this. In this particular case, as I told, there is no coupling, only the coupling is there in the translatory motion or in the tilting motion. So, and this is the damping coefficient, and if we substitute the value, we can get this particular damping matrix. This force vector is given by this, in which force and moments are there. This is the stacking of the response vector. So, the equation of motion, which is like this, for free vibration and undamped system, we can neglect the force and damping, and so we will left with this particular equation, and this particular equation we can able to solve the eigenvalue problem of this, and this will give us the critical speed. These are the 4 critical speed we will get from the eigenvalues. Basically, these are natural frequency. So, the eigenvalue problem will give this natural frequency. Now, for force response, we can able to use this directly without damping or with the damping. So, this is the unbalanced response, where D is this whole matrix. We can able to solve this particular for various values of speed, and we can plot the response like this. So, this is this speed variation at one of the amplitude we have taken here of the displacement, and this is the phase of the displacement. These are the linear plot in x direction and y direction. You can able to see, we can able to get 2 critical speeds here corresponding to the resonance, and there is a change in the phase also. In the other plane also we are getting the same critical speed, because these 2 motions are coupled, and these are corresponding to, you can able to see they are around between 4000 to 6000, they are corresponding to the this first 2. Similarly, we can able to plot the corresponding to the tilting motion in one plane and other plane. Here also we will be getting 2 critical speeds. These 2 are same, and you can able to see they are between around above 7000 to and below 10,000. They are corresponding to this one, these 2. So, you can able to see that through free vibration analysis or eigenvalue problem and through unbalanced response, we are getting the similar critical speeds. Today's lecture, we have seen initially the basic concept of the hydrodynamic bearing, how this particular bearing fluid film forces imparts stiffness and damping, and we have defined the stiffness and damping, both the direct stiffness and cross coupled terms, which couple the motion in 2 planes. With this concept, we have then analyzed a rigid rotor which was mounted on this kind of fluid film bearing, and we derived the equation of motion. Even we solved a numerical example, and we have seen that the free vibration analysis, undamped analysis, and the unbalanced response, they give critical speed calculations nearly same.